We've got another synthesis practice. So we've got 3 or 4 synthesis problems here. So this is going to be a good video to go through and take advantage of that pause button. Before we jump into that, I do want you to review your 5 primary reactions. These are reactions that are critical to being able to adjust and parse out how you're going to move through a synthesis. So make sure you understand these, okay, or can pull them from your brain pretty easily. With that, we can take a look at kind of some synthesis options. So first and foremost, identify what changes happened in your reaction. Once you know what the changes are, match it to a particular reaction type. Okay. Once you know the reaction type, then start doing reagents that could potentially allow that reaction to occur, and keep cycling through this process until you've done the whole synthesis beginning to end. So let's take a hot seconds to walk through one together. So let's look at our reaction. As far as identifying what happened, that's a lovely face down there to be staring at you during this. If we look, we're starting with the pi bond here, okay, and we'll note that it has disappeared. Okay, so we have a loss of a pi bond. We've also regained that pi bond. Okay, so we do have a gain of a pi bond. In that process, though, we also moved. Okay, so we moved from one spot to another. If we think back to our reaction types, the loss of a pi bond would be an addition. The gain of a pi bond would be an elimination. We don't have, and in particular for this one, these are non-polar pi bonds. We don't have a reaction that's going to do both an addition and an elimination at once, okay? Which means we're going to need multiple steps. Okay? Deciding which one to start with is kind of your choice. Most students are a little bit more comfortable moving left to right, so reactant to product, but you could reverse that process as well. Okay? So let's start with the reactant to product. I need to get rid of that pi bond. Okay, so I have to somehow move to a structure where that pi bond is now gone. We could go through and kind of skeletonize our pieces within this that we know changed. So to get rid of that pi bond, I need something here and here to have gotten rid of it. One option is I replace it with hydrogens. Okay, so that would entirely get rid of that. However, that would end me with an alkane. If we look at our final product, we still have chemistry present, which means if I'm going to do an addition of hydrogen, I'm neutralizing the reactivity in the molecule. That's probably not going to be the best bet, okay? At least not at both sites. So now the question, okay, well, maybe I leave something else out here. This is where that movement becomes important. If we look, our chemistry is moving into the structure. If I ran the reaction as I'm showing here in green, I'm keeping the chemistry on the outside of the structure. That doesn't make sense with where my synthesis is moving. Chemistry is moving inwards. So I probably want to place a hydrogen on the outside, which mimics my product. And then I need to somehow keep some chemistry on the inside. Okay? So in running this addition reaction, what are my options? So now I need to think of reagents that would allow me to do that. Okay. If you're stuck with reagents, that's okay. Don't worry about it. Let's go ahead and just continue with this structure. Okay. If you're pulling out the synthesis activity actually addresses some of those potential intermediate structures so that you don't have to envision or make up what that X is. The synthesis activity actually gives it to you. Okay, so we now need to progress as a new reaction. So if we go through and look, again, what have we lost? We're losing chemistry at this position. We need to lose that, and we would still need to gain that pi bond. So again, we can consider how could we do that? Well, the loss of that position and the gain of a pi bond would be an elimination. But would the elimination occur all the way out at that position? Okay, they have to be right next to each other, so no. I could do an elimination reaction, that elimination could result in the loss of that atom X, and that'll drop my pi bond in here. Okay. Again, we could consider possibilities for different structures or reagents, but again, we could be like, well, I don't know that, so I'm going to try and continue on. If we try and continue on, we'll note that we lose the pi bond and we gain a pi bond. Again, doesn't happen all at once, so we could do an addition, giving us reactivity out here. Again, we want that reactivity so that we can then move to the last one, an elimination, to shuttle that reaction inwards, okay, or towards the target that we wanted. And we now have a skeleton process for how we want to do this. It's now just a question of finding out the reagents that allow us to do that. The reagents is the next step beyond this. That requires you knowing those reagents. If you don't, this is where you should be taking advantage of the back of each chapter. In this case, we're doing electrophilic additions electrophilic additions and then just standard eliminations. The standard eliminations that we're running are probably in chapter 9, and the electrophilic additions are going to show up in chapter 10 for these particular additions. There is some potential for radicals. We do need, there's the potential for running a radical reaction within this, and that would jump out to chapter 25, okay? But what I want you to first focus on is these general patterns on how you can move through. Look at those larger structures. Don't worry about the exact details. Worry about the kind of bulk patternings as you move through it, okay? So with that, I'm going to go ahead and say post to Piazza if you've got questions about the exact reagents. I've got no problems going back through and posting that later, but I want you to struggle with that a little bit. Next one, this would be a good time to hit that pause button. Focus on what are the changes, okay? And does a reaction type do all of that? Okay. I'm going to assume you spent some time looking at this. If we go through and start, we really only have one big change, okay, or really two changes. We've got a loss of a hydrogen here so that we could add an OCH3. That would suggest substitution because that's all you're doing, but our substitution reactions require a leaving group, and hydrogen isn't a good leaving group, okay? So we're going to have to throw something else in there. How can we get a hydrogen substitution? That's going to be a radical reaction. So the radical reaction, a radical SN, will substitute a hydrogen. Okay. Hopefully what you remember first with that radical substitution, though, is that that's going to substitute at the most substituted position. It's going to substitute that hydrogen, which does get me reactivity into the structure, but not at the exact position I want. To get it to move downwards so that I can get access to that carbon, I'm going to need to run an elimination reaction. That elimination is going to set up a pi bond in there. That pi bond is now what I could take advantage of to try and get that final substitution. Or sorry, in this case, we would try and do an addition to get us up there. Okay, I'm going to put a question mark there because it's a little bit trickier than that. We can't get it to run in one fell swoop, and that's going to come from understanding some of those reagents, which again, I want you to dig into to see what you can come up with. Okay, see if you can find those possibilities. Process through some options, but ultimately, yes, that last addition is actually a little bit tricky. You're going to have to run a couple different things to get that to work. Okay, so again, look for those larger patterns. Once we start getting those larger patterns down and you're confident in it, that's when adding in the reagents comes in. And again, reagents are a last thing. Okay, you shouldn't be jumping straight to reagents, which is tricky because when you watch someone solve it, that's what they show is the reagent. Oh, I'm going to use this reagent to do this. They're internalizing what they want to do first, then they're throwing the reagents in. So break it down a little bit more. So in this case, yet another synthesis. The reason why I'm throwing this one in is this one is a little bit kind of close to home with the chemistry that we've been studying in this unit. If we go through and see, we've got that pi bond in there. Okay, how could we see, or where have we seen pi bonds show up? Hopefully, wow, I completely forgot how to spell Wittig. Completely, like holy monkeys. Wittig? I think I got it. Okay, so seeing a pi bond show up is kind of a red flag in this unit that you're probably using a Wittig reagent somehow, which means we could try and split this here, and now it's going to come down to the alkyl halide and the carbonyl. Okay, so you should be able to go through and process that. Okay, again, I'm going to be a bit of a jerk and say process that, work at it, see what you can come up with, and we'll go ahead and bring in another one. We've got another carbon-carbon formation. There's clearly a new carbon-carbon bond here. That carbon-carbon bond is new, which fits in the pattern of our Wittig or our Grignards. So I would lean towards a Grignard for synthesis number 2. Okay, either one's work, or either one works, either Wittig or Grignard. Go ahead and attempt those. So that means hitting that pause button and seeing what you can come up with. And then what I will go ahead and do is break apart this one into 2 constituent pieces. So my first swing, 5-membered ring, we'll split that out, carbonyl and our alkyl halide. 1, 2, 3, 1, 2, got the carbons all right. Okay, and then that would work. How are we going to run this reagent wise? So we would start with this guy, step 1, pH3. That puts the pH3 in place of the bromine. 1, 2, 3, 4. Why does that look weird? It's right. Now my butyl lithium. The butyl lithium comes in, gets me that carbon nucleophile. 1, 2, 3, 4. pH3 with my negative. Now I can bring in that last step, the carbonyl. That's where we form that goofy intermediate, and we would end with our final product. Okay, so in this case we just did it as kind of a simple synthesis because we're really only focusing on forming one bond. The steps that we had to run behind it were just kind of necessity of the Wittig reaction itself. There weren't extra limitations on this, like for instance that you had to use X number of carbons in your skeleton structure or your starting structure. So this would satisfy what you would need as far as this question is concerned. Other ways we could do it would be like you can't start with more than 5 carbons. Okay, that gets a bit obnoxious because then that means this whole starting material you can't use, or you would have to come up with some way of making that from a 5-carbon structure. That's harder than I want right now, so don't stress on that. Okay, for the next one, if we're looking at this process, we wanted, I said as a suggestion, a potential for a Grignard, and I said you could do it as a Wittig too, so I'll show them both. If we were to go through and do a Grignard, the first thing we would do with our alkyl halide is add the magnesium. CH3, CH2, CH, CH2, CH3. There's our MgBr. Okay, so really what we're doing, let's see if I can erase that gently. That sort of worked. We're forming our negative, man, that is, I apologize, let me try that again. Lone pair, negative, there's our MgBr. We would need to react this with a carbonyl. The carbonyl has to have these pieces, so we're looking at the aldehyde, CH3, only 2 carbons. Grignard comes in, attacks, bumps that up. This is going to get us our carbon backbone, which has 5 carbons, 1, 2, 3, 4, 5. Okay. There's the new bond, which I guess we could show in green because I started it that way. Here's our alcohol. And there's that CH3. We aren't quite there yet because we need to get rid of that alcohol. Chemistry that you know at this point, you could try and do an elimination. In the elimination, you would go through, form the most substituted with our CH3. Once you've done the elimination, you could then do an addition of just H2 and you would add your 2 hydrogens to get to that final answer. And there we are. Okay. That elimination, as far as reagents go, we'd be adding a stupidly strong acid, H2SO4, to make that water or make that OH a good leaving group, and we'd probably want to add some heat to help facilitate that elimination. Okay. The addition of the H2, that's H2 over platinum or palladium. We aren't looking at anything fancy for that one, but that's how that one would work. Okay. There are other ways that you could convert that OH into a better leaving group, but all that kind of fun jazz to get the elimination. This just happened to be one of those syntheses. I did say you could do it as a Wittig, so let's take a look at the Wittig. The Wittig is going to need to get that double bond, right? We're still going to have to add that H2 across it. So we do our PPH3. 1, 2, 3, 4, 5. There's our PPH3 with our butyl lithium. We get our negative carbon, PPH3, and then we would react that with our carbonyl. Whoops, too many carbons. And whoops, there's stuff underneath it. Carbon 1, carbon 2. And we'd get our elimination or our nucleophilic addition to get us that alkene, and then we could do the H2 with platinum. For those of you being like, well, this synthesis has a secondary alkyl halide, isn't it less likely to run under the Wittig? Yes. Okay, good observation, I like that. But again, we're just trying to follow through those patterns and see what jumps at us to be able to move through it. Okay. So hopefully that helped. If you've got questions, remember, take advantage of the discussion boards and email and office hours and all that fun jazz, but that should get you kind of moving as far as synthesis goes. And with that, thanks for watching. Assuming my mouse works.